Hello, everyone, and welcome to week one in database systems. My name is Dr. Alan Dennis. This week, we'll be going over the assignments, talking about chapters 1 and chapters 2. First, the assignments. So this week is all about kind of getting started and getting to know each other. To that end, you're asked to introduce yourself with a discussion board post. It is not graded, but it is highly encouraged. The second thing you're to do is to have a discussion related to both chapters 1 and chapters 2, each of which are due by the end of the week. Also, be sure that you complete the University of Cumberland's plagiarism pledge, and it is due also by the end of this week. If you fail to do participation during the first week of course, you may be dropped from the course, so be careful of that. For reading for this week, we're going to be going over chapters 1 and chapters 2, both of which kind of start introducing the concepts of databases, who uses databases, and some of the general concepts and architectures that are related to that topic. The objectives for chapter 1 are listed on the screen. The basic idea of the first chapter is to kind of introduce the concepts of what a database is, why you use them, what they do. And then we move into more detail in the second chapter, going into things like schemas and architectures and how you actually implement some of those things in a real database management system. So again, the first week you're asked to introduce yourself to the class. Tell us a little bit about yourself, what you expect to learn from this course, maybe a bit about your background, your interests, and you're required to create your own initial thread in order to do this. Just don't respond to others, but create your own. This is not graded, but it is required. The second thing that is due this week is the discussion number 1 for chapter 1. You're asked to give examples of systems in which it may make sense to use traditional file processing instead of a database approach. You're asked to do so in 250 to 300 words. Also, be sure that you respond to your classmates. Your initial post is to be done by Wednesday at midnight Eastern Time. And make sure that you're engaging actively in the discussions. That's kind of the purpose of those, is to simulate the conversations that would normally happen in an on-ground classroom. Your second discussion is related to chapter 2. In chapter 2, you're asked if you were designing a web-based system to make airline reservations and to sell airline tickets, which database management system architecture would you choose from section 2.5 and why? Why would the other architectures not be a good choice? Again, you're asked to respond to that in 250 to 300 words. Make sure that you do so by Wednesday and ensure that if you're citing, which you likely will be, that you do so in APA format. Avoid direct quotes in your posts as well. It's potentially a dangerous thing and it's often done incorrectly. So in general, summarize rather than quoting directly. You're also asked to complete the University of Cumberland's plagiarism pledge contract. This is required, and you are to basically complete a simple tutorial, take a quiz, sign and upload the contract, and it must be submitted before other written assignments will be accepted for credit. You feel free to research this topic in the links provided below. But understand, though, plagiarism will not be tolerated in this course, and if you commit the offense, you will fail the course, most likely. So do not plagiarize, do your own work, make sure that you cite the sources you use. Moving into chapter 1, in databases and database users. The basic learning objectives are to talk about the types of databases and database applications, go over some basic definitions, talk about typical database management system functionality, examples of a database, in this case it's a university-based architecture or example, the main characteristics of the database approach, the types of database users, the advantages of using the database approach, historical development of database technologies, and extending database capabilities, and when to not use a database is the final topic. Moving into types of databases and database applications. There are traditional applications which generally are storing numbers and text inside of a database. However, there have been recent advancements in technology in the past 10 to 20 years, relatively recent, that include things like multimedia databases, graphical or geographical information system, GIS databases, biological and genome databases, data warehouses, mobile data warehouses or databases, and real-time and active databases. The first part of this book focuses on traditional approaches. And you want to take a look in the later chapters for some more recent applications of databases. Also, in recent developments, there have been social networks that started capturing tremendous amounts of data about people, what they do, and communication between posts and so on. This is referred to, generally speaking, as Web 2.0, and it started the trend of users being the creators of data, not the consumers of it. So whenever you go to Facebook, most of the stuff you're seeing there came from other people, not from Facebook itself. That was a dramatic shift that happened around 2000 or so, give or take. And it has basically shifted the pattern to where organizations create a framework for storing data, but not the content itself. Because of this, there's been a tremendous amount of data being generated, and so it has changed the way that we do our data processing. All of the activity that goes on is considered data, some of which will be more structured than other. We'll get into that later, but it all is data. Search engines also were one of the things that started pushing the boundaries of data processing and data storage. And that's because they do things like crawl an ever expanding internet and find things that might be of interest to you. And more importantly, figure out what things might be of interest to you, not just all the things that exist. New technologies are also emerging in so-called non-database software vendors to manage vast amounts of data generated on the web. Big data is a perfect example of this. Big data storage systems involve large clusters of distributed computers. We'll talk about that in chapter 25. NoSQL is an exemplar of that sort of approach where data is stored in a schemaless or schema on read fashion using different sort of concurrency control models, and we'll talk about those as well. A large amount of data now resides in the cloud, which is computational centers in data centers that are outside of an organization, accessed typically over the internet, to the point that traditional data centers are becoming a thing of the past. And there's lots of reasons for that, a bit beyond the scope of this course, but cloud computing has revolutionized every aspect of this industry, including databases. So some basic definitions. We need clear definitions when we talk about things so that we know what we're talking about. A database is a collection of hopefully related data. I say hopefully because it depends upon how that database was created. A data is well-known facts that can be recorded and have implicit meaning, meaning it's something that can be ascertained and has value and can be determined to mean something unto itself. Mini world is some part of the real world about which data is stored in a database. For example, student grades and transcripts at a university. You can almost think of this as a form of simulation of a very low granularity. You're taking something that exists in the real world and producing a digital copy of it in a virtual sort of world that happens to be some relatively simplistic values such as your name, your grade, and so on. Database management systems are software packages and systems that facilitate the creation and maintenance and management of computerized databases. Databases are not necessarily digital. We think of them that way, but a database could be a filing cabinet. That is technically a database. But whenever we talk about databases in the scope of this course, we're talking about electronic databases that are utilizing computers as the storage and retrieval mechanism. DBMS software together with the data itself is considered a database system, and oftentimes maybe the applications that are interacting with that data may be included as well. The impact of database and database technology. In business, it impacted all elements, be it banking, insurance, retail, transportation, healthcare, manufacturing, service industries, financial, real estate, legal. Basically, it's hard to imagine a industry or field within an industry that has not been impacted by the emergence of electronic databases, especially those that are accessible at relatively low cost and with low effort. There was a time that these things did not exist, and in that time, things moved at a much slower pace, and database, what we think of as a database today, would cost tremendous amounts of money to do. That all changed somewhere in the mid 80s whenever personal computers came out and things like DBase came out, one of the first database programs. And it basically made it such that now we cannot imagine a world without databases. This is a simplified database system environment. The elements here that are of interest is there's several. I'll turn on the laser pointer and point at them. Users are programs or things which interact with the database management system itself. So the entire data system is somebody is going to be using it, be it a person, be it another program, be it some form of integration. Things don't exist without somebody using it. So it's either going to be people running queries or other programs that are interacting with it as a data store. There's also application programs and queries that are associated with a database. Those are things that might be something that runs internally ever so often that does some unit of work. It might be things that make it much easier for people to find the things that they're looking for. Could be lots of different things, but there's generally speaking a layer of some sort of program that's involved. There's software that is to process those queries and programs, and it does lots of stuff to figure out how to do so in an effective and efficient way. And then you have things that actually go and get the data from some actual physical data stores, typically on a disk of some sort. So you need some mechanism to access both the stored data and a much smaller but very important a set of data as well, which is metadata. Meta means things about. So metadata is data about data is the way to think of it. So it allows you or allows the system to know what data is stored and how to access it and what might be perhaps the most efficient way to do the querying and so on. So those are the high level elements of most database systems. Typical database functionality. Generally speaking, you define a particular database in terms of its data types, structures, and constraints. You construct or load the initial database contents on a secondary storage medium. So typically it comes from somewhere else. You manipulate it in some fashion, typically doing retrieval, which is where you do queries and generating reports, modification, inserts, deletes, updates, potentially depending upon the type of database, and accessing the data through some sort of application layer, be it a web application or something else. You typically also process and share and do so in a concurrent fashion so that a database is serving multiple users at the same time. And concurrency control, meaning that those things that are interacting, the processing that are occurring, the querying, and so on, does not interfere with each other in a negative way. Continuing our discussion of application activities against a database, applications typically interact with a database by generating either queries or transactions. A query is something where you're trying to retrieve something. A transaction is where you're essentially wanting to record something or update something. So it's essentially the difference between if you were using a notebook as your database, a query is whenever you're scanning it to find something, a transaction is when you're writing or editing something that's already been written down. You want to make sure that only authorized users access the data which they are allowed to access. There's two or three things bundled up in that statement. One, you need to know who they are, so you need to know their identity. The second thing is you need to know what their authorization is, so what they're allowed to do and what they're allowed to have access to. And you must keep up with changing user requirements against the database. There's a concept of something called schema evolution, where things change over time. Something that is alive will change. So if an organization needs to capture some new information, allow you to search for something new, then you need to make sure that the database system is able to accommodate those changes. Database management systems may also protect or secure measures to ensure that there's unauthorized access. Almost everything expects that to be the case today, although there may be situations where the data is of low risk or value and you're not as concerned with somebody having access to it. They actively process and take internal actions on data. They present and visualize data, so you may potentially be able to do visualizations through some sort of visual exploration tool. You typically perform maintenance on the data and the database and associated programs over the lifetime of the database. This is generally, these whole things are called together, database software and system maintenance, an important aspect of all database systems. An example of a database with a conceptual model, starting off on the first. Again, we had this conversation earlier about the idea of a mini world. Mini world is a small representation of something that exists in the physical world, but is simplified so that it's easier to understand and to capture those elements of interest. So imagine that you're part of a university's environment. You have students, you have courses, you have sections that are part of courses, and then you have academic departments, and then you have instructors. Those are essentially the entities, the things of interest in this universe. So there are some relationships between these particular entities or items which we talked about. You have sections are of specific courses. So a course has multiple sections or one or more sections. A student can take a section which is in turn related to a course. Courses have prerequisites of other courses. So in order to take one course, you might have to completed a previous course. Instructors teach sections, courses are offered by departments, and students major in departments. Note that the above entities and relationships are typically expressed in a conceptual data model. We'll talk more about that later on when we talk about entity relationship data modeling in chapters 3 and 4. Here's an example of this simple database that we talked about. Generally speaking, when we talk about data, it's going to be represented in a tabular fashion, and that's what this is a grid with you've got the columns, which are the attributes of interest, and then each one of the rows is a record that exists within that column. So you have a section identifier, so section 85 of course number Math 2411, it's offered in the fall, and in the year '07, and the instructor was King. So this is one record within this simple table. And that's the words that we're using. I'm starting to teach kind of the nomenclature, columns, records, and the whole thing being a table. Another example, this would be grade report of what a student number inside of a section earned in that particular section. Prerequisites where you're basically saying the course number is 3380. In order to take it, you had to have taken CS 3320 and so on. So the basic idea here, again, columns, a table with two columns, one being a course in the course that's required to be taken prior to that course, so the prerequisite for that course. So generally speaking, databases are somewhat self-describing. There's a catalog that's used to store the descriptions of a particular database, the data structures, the types and constraints, and there may even be additional data associated with it that is actually truly a textual description. This whole set of data is called metadata, that is data about data. Not every table or not every database management system utilizes that. That's what the asterisk down here is saying at the bottom, because there's some things like NoSQL databases that may not necessarily have metadata, or that data may be something that is inferred on use, not necessarily whenever you're creating the database. And this information as a whole, though, allows the database management system to work with different database applications. So it's a way of being able to use the same basic engine, the same database technology, to solve lots of different problems because you know what those problems are based upon the catalog. And there's an insulation between programs and data, and this is called program data independence. This allows changing the data structures and the storage organization without having to change the database management systems, the access programs. This is also sometimes called abstraction, or using an interface of some form to enable this sort of capability. But the basic idea is that the data that you're storing should be able to be stored in such a way that you could potentially change out the database management system and the users of that data not be affected. Moving on to figure 13.1, an additional sort of list of those and something that might come out of a database catalog of the relationship name and the number of columns associated with that relationship. So there's a relationship around student, course, section, grade report, and prerequisite. Moving into what are columns, and columns are something that typically has some form of a data type. It has a name as well, and it belongs to something, be it a table or something. So it's an attribute that's associated with a given, typically table. Could also be associated with a relationship. Data abstraction is in a data model is used to hide storage details and present the user with a conceptual view of the database. It also refers to the program model construct rather than the data storage details. Support of multiple views of the database or of the data allows you to, each user can see a different view of the database. Each describes only the data that is of interest to that user, and take that a step further. Sometimes they can only see that stuff which they're allowed to see. That's oftentimes referred to as row level security. Basic idea is that sometimes you don't want you and I to see the same things. And in that scenario, I might see 5 rows and you might see 4. So it's based upon who you are determines potentially what you see. Sharing of data and multi-user transaction processing allows for a set of concurrent users to retrieve from and update the database. What that means is that you're allowed to have things updating and reading at the same time. This is necessary because of the load that most databases are under. A concurrency control within a database management system ensures that that a transaction is correctly executed or aborted. You want it to go all the way through or not at all. You don't want some sort of a partially completed transaction to occur. So if you're subtracting from one table and inserting into another table, you don't want to do just the subtraction and not the insertion. Those two things happen together, and that's what's termed a transaction. A recovery subsystem ensures that each completing transaction has its effect permanently recorded in the database. OLTP, online transaction processing, is a major part of database application that allows for high degrees of concurrency per second. Database users, typically you speak of them in terms of either personas or actors. These are the people who actually use and control the database system, and those who design, develop, and maintain database applications. Actors on the scene, a persona, there's lots of other words. Those who design and develop the database management system and related tools, and the computer system operators are sometimes called workers behind the scene. Maybe you might hear that nomenclature and you may not. There's typically an administrative sort of capability, and then you have typical database users, and there's a clear delineation between those in most systems. So a database administrator is responsible for authorizing access to the database, for coordinating and monitoring its use, acquiring software and hardware resources, controlling its use, and monitoring the efficiency of operation, whereas a database designer is responsible for defining the content, the structure, the constraints, and functions or transactions against the database. They must communicate with the end users and understand their needs, and it's based upon those needs that things occur. A database designer is responsible for taking a set of requirements and implementing some form of a solution. Continuing the discussion on actors on the scene, you have system analysts and application developers. These are categories that account for or accounts that are a very large portion of the IT workplace. These are people that are system analysts, or they understand the user requirements of naive and sophisticated users, develop application or design applications including CAN transactions to meet these requirements. Application programs meet these specifications developed by the analyst and test and debug them before deployment. Business analysts are those which basically can analyze vast amounts of data in real-time data and then make decisions based upon it. And sometimes these are particular roles, but you may have a person who may do multiple roles. Actors on the scene, end users, these are the users of the database that typically run the queries or cause the queries to be ran, either by running them explicitly or running a report. They may update the content. They may be able to be categorized into casual, which means they have access to the database occasionally whenever they need it. Naive, which basically means they aren't all that skilled. They may have some idea, but not necessarily a high degree, and may be able to run transactions or queries, but not necessarily author them. They may be using mobile apps to access data. A bank teller, reservation clerk, are essentially those who you can think of in this particular group. Social media users are another example where you're indirectly causing something to be done inside of it, but you're not necessarily aware that you are. A sophisticated user, there's a smaller subset. These are business analysts, scientists, engineers, and there are others who are thoroughly familiar with the system capabilities. They may use lots of different software packages to do their work. And then there's standalone. This is basically personal databases ready to use, packaged applications, perhaps a tax program. If you're using one that's offline, so you've installed a piece of software to do something, maybe you're keeping track of your music collection if you're doing it offline. But it's something, maybe a database of your personal photos if you're not storing them in the cloud. But the number of standalone databases has become much smaller as the world has become more connected. Moving on to actors behind the scene, system designers and implementers design and implement database management system packages in the form of modules and interfaces. They test and debug them, make sure they're working correctly. They must interact with application, language compilers, and operating systems. Tools developers define and implement software systems that are essentially tools for modeling and designing databases, performance monitoring, prototyping, testing, test data generation, user interface creation, simulation, and so on. Each one of these is getting to be a smaller set. There's a whole lot more system designers than there are tool developers. Tool developers are going to be probably either doing something in an open source project or they're going to be working for a large software company. Operators and maintenance personnel, they manage the actual running and maintenance of the database system and software. This is something that's generally considered operations, and it's kind of merged over the years with this whole emergence of things called DevOps, which is a combination of development and operations being done by essentially the same people in the same team. And there's lots of reasons for that, but it has a high sort of association with NoSQL databases as well. Advantages of using a database and using the database approach. You control redundancy in data storage and in the development and maintenance efforts. You share data across lots of different people. You restrict unauthorized access of data. Only the DBA staff uses privileged commands and facilities. You provide persistent storage for programming objects, and typically there's this concept of object relational modeling and mapping. The idea is that if you have a program that's running, it typically will store data in some fashion that can be stored in a database, and there's a transformation involved. Object-oriented database management systems, less common than they were a few years ago, still exist, kind of been replaced by the whole concept of NoSQL, where you store data in the format that you're actually using it. Providing storage structures such as indexes for efficient query processing. We'll talk about that in chapter 17. Provide optimization of queries for efficient processing, provide backup and recovery services, very important, especially if the data has value. Multiple interfaces to different classes of users, so people may see something in a slightly different way depending upon who they are. And then presenting complex relationships among data, enforcing integrity constraints on the data, making sure that it looks like what it's supposed to look like, making sure that if you say that you're referencing a particular course as a requirement in the prerequisites table, that course actually exists. Draw inferences and actions from the stored data using deductive and action rules and triggers. Kind of falls into the category of something called data mining. And then application implications of using the database approach. Potential for enforcing standards. There is very crucial for success of database applications in large organizations. Standards refer to making sure things are named correctly, stored correctly, way that a particular screen might be structured, the report structures and the metadata. It could be as simple as something called master data management, where whenever you have perhaps gender is stored in one of your tables, that a given gender, say female, is always mapped to the same value, say 1. If you have inconsistency amongst different storages of the same attribute, essentially, you can have lots of challenges when you start pulling them together. And that's where the concept of standardization comes to play. Reduced application development time potentially increases, it's an incremental time to add new applications to using a database. Depends upon the rigidity of the database environment. And again, that's where NoSQL kind of came to play, is it became much quicker to add things than traditional relational database management systems. Some additional implications of using databases approaches. They provide for flexibility to change the data structures. Data structures can evolve over time. That's that schema evolution I mentioned earlier. As new requirements are defined, availability of current information, it's extremely important for online transaction systems such as shopping, airline, hotel, and car reservation systems. So making sure that the information that you're seeing is the current and correct value, and there's almost no lag in something being distributed across the environment. Economies of scale, sometimes you can have less waste. Whenever you have wasteful overlap of resources and personnel can be avoided by consolidating data and applications across departments. So rather than having each department have their own database server, you have one somewhat slightly larger database environment and everybody uses a shared resource. That's kind of the whole concept of cloud computing, doing economies of scale and sharing across lots of different people. And that's part of why you will oftentimes use a database in the cloud as well. Historical developments of database technology, early database applications, the hierarchical network node models were introduced in the mid-60s, dominated for quite a while based upon the capabilities of hardware at the time. A bulk of the worldwide database processing still occurs using these models, particular hierarchical models using IBM's IMS system. The relational model based systems, relational model was introduced somewhere in the 70s, was heavily researched and experimented with IBM research and several universities. Relational database management products emerged in the early 80s. I would say at this point, though, that's going to be what most processing is occurring, not necessarily in a hierarchical model, unless it's in a big data store. Object-oriented emerging applications. Object-oriented database management systems were introduced in the 1980s and early 90s. They catered to the complex data processing in lots of fields, including computer-aided design. They really never caught on, and in part, the performance was an early challenge. Many relational database management systems have incorporated object-oriented concepts, leading to a new category called object relational database management systems. Extended relational systems add further capabilities for things like multimedia data, XML, text, and so on. And then the database on the web and e-commerce applications. Web contains data typically in HTML or XHTML with links amongst the pages. This has given rise to a new set of applications with standards like XML, which will be covered in Chapter 13. Script programming such as PHP, JavaScript, Node, JS, lots of Angular, lots of emerging ones. Allows for the generation of dynamic web pages that are partially generated from a database, or maybe they're getting their data from the database in an asynchronous fashion. They also allow database updates through web pages. That's become kind of the norm, typically through a web service of some sort. You load some code onto your browser. It retrieves some data from a database indirectly, often through an API, and then you do something with it. Extended database capabilities. There's new functionalities are being added in the following areas: scientific applications, physics, chemistry, biology, genetics, earth and atmosphere science and astronomy, XML, image storage and management, audio and video data management, data warehousing, data mining, spatial data management and location-based systems and services, time series and historical data management. Has given rise to new research and development incorporating new data types, complex data structures, new operations and storage, and indexing schemes in databases. The background since the advent of the 21st century, the first decade of the 21st century has seen tremendous growth in user-generated data and automatically collected data from various applications and search engines, typically in the form of log files or content that users are creating. Social media platforms like Facebook and Twitter are generating millions of transactions. It's probably more than that these days, a day. And businesses are interested in tapping into that so that you can understand your users. So if you know what somebody posts about, you might know what they're interested in buying, and that's very valuable. Cloud storage and backup is making unlimited amounts of storage available to users and applications. Essentially now, whenever you can pay for it, you can get it. And that's become the norm. The emergence of big data technologies and NoSQL databases, new data storage, management, and analysis technologies were necessary to deal with the onslaught of data that is of the petabyte and exabyte scale, and we started calling that sort of things big data. Hadoop is one of the first sort of things to kind of come out. It came out of Yahoo originally as a side product from one of the employees that they had acquired. It enabled something called MapReduce, which is a way of doing programming in creating distributed concurrent software applications in a much simpler way. That was based upon some concepts from Google. Also, there was this concept of Google File System, which in turn became the Hadoop file system or gave rise to it. And this whole thing kind of enhanced the creation of big data technologies. And then it was taken to another level with the advent of Spark-based technologies. Spark relied on memory-based computation in a distributed fashion to do things roughly 100 times faster than MapReduce. NoSQL databases, and not only SQL is not really an accurate way of stating. NoSQL implies originally that they did not utilize SQL as the query structure, although many NoSQL databases started adopting it, or SQL sort of languages for querying and operation. So some people try to argue it's not only SQL. The capitalization's wrong. It's NoSQL is how it's capitalized. But the basic idea, though, is that it is a non-relational, potentially, data store that stores either documents or column-oriented data or data in slightly different ways than traditional relational data for lots of good reasons and high performance and distributed fashion. We'll talk a bit about that in chapter 24. When should you not use a database? And not knowing when to do something is as important as knowing when to do it. The main inhibitors is potentially cost. There's potentially a high investment, especially if you buy a commercial database system. You may need hardware if you're not doing cloud computing. There may be some overhead for providing the generality, security, concurrency control, recovery, and integration functions. You're going to have to do some designing, right? And so you want to make sure that it's done in a correct way, that you think about operations and so on. It may not be necessary if the database changes and applications are simple, and it could be that you may be better off doing file processing than you are doing a database, and especially if things are not expected to change. And if you're going to be not going to be using multiple users, so if it's a single user scenario, may not need a database because you may not be as concerned about concurrency control. And it may not be feasible if you're using embedded systems, although they've gotten really tiny, so probably still you could find some form of a relational data store even in embedded systems. If there are stringent real-time requirements, you may need a real-time database, not necessarily a relational database management system. And if the database system is not able to handle complex data because of the modeling limitations, so maybe something more in the big data, NoSQL world is more appropriate. If the database users need special operations that are not supported by database management systems. So in summary, we talked about the types of databases and applications. We went over the basic definitions. We talked about typical database management system functionality, gave an example of a database, the main characteristics of the database approach, the types of database users, and the advantages of using a database approach. We talked a bit about the history of database technologies, how those things have been extended over time, and then we talked lastly about when to not use a database. And with that, we reach the end of chapter 1.